Right now, 16 billion miles from where you're sitting, a machine the size of a compact car is screaming into the void. Its transmitter puts out 22.4 watts, less than a refrigerator light bulb. By the time that whisper crosses interstellar space and reaches Earth, it arrives as a signal 20 billion times weaker than the electricity needed to run a digital wristwatch, 1/10 quadrillionth of a watt. Its onboard computer runs on 69 kilobytes of memory. Its processor executes 8,000 instructions per second, nearly 2 million times slower than your phone. And last year, when that computer crashed 16 billion miles from the nearest repair shop, a team at JPL performed remote brain surgery with a 47-hour round trip for every single command. The data rate is 160 bits per second, 6 million times slower than your home internet. The signal power at Earth is measured in attowatts, 10 to the negative 18th watts. And yet, for 48 years and counting, that link has held. This is the story of the farthest machine in human history, the physics that say it shouldn't still be talking, and the engineers who refuse to let it die. The machine at the edge of everything. As of April 2026, Voyager 1 sits at 172.59 astronomical units from Earth, 25.8 billion kilometers, 16 billion miles. It is hurtling through the interstellar medium at 17 kilometers per second, 38,000 miles per hour, and it is never coming back. A radio signal traveling at the speed of light takes 23 hours, 29 minutes, and 27 seconds to reach Voyager. One way, a round trip takes 47 hours. And in November 2026, the spacecraft will cross a threshold no human object has ever touched, one full light day from Earth. After that, every command will take more than 2 calendar days just to be acknowledged. Despite that distance, the spacecraft is still returning science data from interstellar space, but it almost didn't survive to see this milestone. Brain surgery at 16 billion miles. On November 14, 2023, Voyager 1 stopped making sense. The Deep Space Network could still detect a carrier wave, but the data stream had devolved into alternating ones and zeros. Gibberish. The spacecraft was conscious but incoherent. JPL traced the fault to the Flight Data Subsystem, the FDS, the computer responsible for packaging all data before transmission. In March 2024, engineers sent a poke command to force a full memory dump. The diagnosis: 3% of FDS memory was corrupted. A single chip had died, likely a cosmic ray strike or simple degradation of 46-year-old silicon. The FDS has just 8,198 words of memory, 69.63 kilobytes total. No single unused block was large enough to hold the relocated code. So JPL's engineers fragmented the critical telemetry software into smaller pieces, adjusted assembly-level memory pointers so the fragments still executed in sequence, and hid them in disparate corners of the surviving memory banks. On April 20, 2024, after a 45-hour wait, engineering data returned. By May 19th, science data was flowing again. Remote brain surgery, 16 billion miles away, on a machine built before Star Wars. But it wasn't over. In late October 2024, a fault protection system triggered when an onboard heater drew too much power, automatically shutting down the primary X-band transmitter and switching to a backup S-band transmitter that hadn't been used since 1981. Ground stations detected the faint signal, a mere 40 bits per second, confirming the spacecraft was alive. Engineers spent weeks carefully resetting power states before safely restoring the X-band. Then in May 2025, they revived backup attitude control thrusters that had been dormant for 21 years, bypassing primary thrusters whose fuel lines had clogged with silicon dioxide residue. The physics that shouldn't work. The fact that we can hear Voyager 1 at all is, on paper, absurd. A 22-watt transmitter pushing a signal through a 3.7-meter dish across 16 billion miles of vacuum. The inverse square law shreds the signal. Over 300 decibels of path loss at 8.4 gigahertz. When the wavefront reaches Earth, the received power is approximately 10 to the negative 16th watts. In decibel milliwatts, that's between negative 156 and negative 161 decibel milliwatts. A Bluetooth device operates at negative 70 decibel milliwatts. A cell phone dropping a call registers around negative 100. Voyager's signal is billions of times weaker, deep in the attowatt regime. NASA's Deep Space Network catches it with 70-meter parabolic dishes, 230 feet across, at 3 complexes spaced around the globe: Goldstone, Madrid, Canberra. Cryogenically cooled amplifiers, submerged in liquid helium, drop receiver temperatures to 15 Kelvin, pulling the signal from the thermal noise floor of the universe itself. The data rate tells the rest of the story. During the Jupiter flyby in 1979, Voyager transmitted at 115 kilobits per second. Today it runs at 160 bits per second, over 6 million times slower than a modern gigabit connection. 48 seconds to send a single telemetry frame. Forward error correction, Reed-Solomon outer code and convolutional inner code lets ground decoders probabilistically reconstruct bits lost to cosmic noise. Every decibel of coding gain keeps the link alive. Dying by 4 watts a year. Voyager 1 runs on the slow death of plutonium-238. 3 radioisotope thermoelectric generators convert heat from alpha decay into voltage through silicon-germanium thermocouples. At launch, they produced 470 watts. Plutonium-238 has a half-life of 87.7 years. The output never stops falling. Compounded by thermocouple degradation, the spacecraft loses 4 watts every single year. As of 2026, it's running on roughly 200 watts. JPL has spent 2 decades playing orbital triage, disabling heaters, killing redundant systems, permanently shutting down instruments to save watts. The plasma science instrument died in 2007. The cosmic ray subsystem, the detector that confirmed Voyager left the heliosphere, was shut down in February 2025. The low-energy charged particle detector is scheduled for deactivation by the end of 2026. After that, only 2 instruments remain: the magnetometer and the plasma wave subsystem. Engineers have even gambled by turning off heaters entirely, discovering the hardware survived at temperatures far below tested minimums. JPL projects at least 1 instrument will remain operational into the early 2030s. After that, the power curve drops below what the transmitter and central computer need, and then silence, permanent silence. What the void actually sounds like. On August 25, 2012, Voyager 1 crossed the heliopause at 122 astronomical units, the boundary where the solar wind is overwhelmed by the interstellar medium. It became the first human-made object to leave the sun's protective bubble. The crossing was confirmed not by the broken plasma science instrument, but by the cosmic ray subsystem, which recorded a sudden sheer drop in solar particles and a 3-fold spike in galactic cosmic rays from exploding stars elsewhere in the Milky Way. What it found defied the models. The magnetic field magnitude spiked upon crossing, but the direction refused to rotate toward the galactic field as predicted. It remained stubbornly aligned with the sun's field. That full rotation still hasn't occurred, though data suggests it's slowly turning toward galactic north. In 2021, Cornell astronomer Stella Koch-Ocker discovered that Voyager's plasma wave subsystem was detecting a constant, faint narrowband emission between solar shock waves, an interstellar drone, described as a quiet, gentle rain permeating the space between stars. The frequency shifts with plasma density changes, revealing the interstellar medium is unexpectedly structured, turbulent, and denser than predicted. When Voyager 2 crossed the heliopause 6 years later on a different trajectory, it found what Voyager 1 hadn't: a leaky boundary, with solar particles trickling millions of miles into interstellar space. It also detected plasma exceeding 54,000 degrees Fahrenheit and a magnetic field stronger than any model predicted. The void between stars is not empty. It's a pressurized ocean pushing against our solar system from every direction. 69 kilobytes and a golden record. Voyager's computers were designed before commercial microprocessors existed. Discrete transistor-transistor logic, a master clock at 4 MHz, effective processing at 250 kHz, 8,000 instructions per second. A modern smartphone does 14 billion. Your phone is 2 million times more powerful than the computer navigating interstellar space. Bolted to the spacecraft is the Golden Record, a 12-inch gold-plated copper phonograph carrying 115 images, sounds of thunder and whale calls, greetings in 55 languages, and a 90-minute playlist of Earth's music. The cover is electroplated with uranium-238, half-life of 4.46 billion years, so any civilization that finds it can calculate exactly how long it's been drifting. In June 2024, Dr. Ed Stone, Voyager's project scientist from 1972 to 2022, passed away at 88. Under his leadership, the mission rewrote our understanding of the outer solar system. As Linda Spilker, the current project scientist, puts it, "Every minute of every day, the Voyagers explore a region where no spacecraft has gone before. Every day could be the last, but every day could also bring another interstellar revelation." The silence that's coming. In 2025, the White House proposed a 47% cut to NASA's Science Mission Directorate that would have terminated missions like Voyager. A massive public advocacy campaign led Congress to reject the cuts entirely. The final 2026 budget allocated $24.4 billion for NASA, preserving the Deep Space Network and JPL staffing through the end of the Voyager mission. No spacecraft will ever catch Voyager 1. New Horizons, launched with the highest initial velocity in history, got only one gravity assist from Jupiter. Its escape velocity is 13 kilometers per second. Voyager, boosted by Jupiter and Saturn during a planetary alignment that won't repeat for a century, travels at 17. It will remain the most distant and fastest human-made object indefinitely. Sometime in the 2030s, the power will drop below critical limits. The DSN will point its dishes at the coordinates. Silence. But the spacecraft will keep drifting at 38,000 miles per hour. In 40,000 years, it will pass within 1.6 light-years of the star Gliese, 445. Because interstellar space is functionally frictionless, the chassis and the golden record will survive for billions of years, orbiting the center of the Milky Way long after the Sun has swallowed the Earth and collapsed into a white dwarf. It will outlive its creators, their planet, and their star. A permanent, silent testament that we were here. Right now, a 22-watt transmitter 16 billion miles away is pushing a signal at 160 bits per second. That signal is 20 billion times weaker than a wristwatch battery. And a team of engineers in Pasadena is listening, pulling meaning from the faintest whisper ever detected by human technology.